So let's try another type of analysis. We can do some stuff pretty easily. We already have, say, the centroid of each one of these. If we deconstruct that point, we can use it to determine height values for these. So let's remap, say, the z of this component. Just like we did before, we'll say smaller than a certain percentage, say 50%. So we can turn that up or down to see the height associated with that. Now we can also test the surface for something like curvature. We've done that before. Or we would say surface closest point. Use that centroid. And then we would use the UV of that to get a principal curvature of that surface. We use this surface. That UV point. Then we can use, say, like the minimum curvature direction. Let's plug that into say our remap number sequence. And let's see. So you have major curvature in those areas where you're getting the biggest fold in there. And there's a big jump between 0.8 and 0.9. See if the maximum has a difference. A little less noticeable. Let's give it a little more fine tuning of this so we can see if we would get good values. Yeah. So with a couple more decimal places, you can see where there's high curvature in that surface, right? So you could test all different types of data. You have z value, you have curvature, you have distance, distance to curve, distance to point. Let's try something like slope as well. We'll group that. So one thing I can start doing is, say, getting the normal of this surface. So I already have, say, the surface closest point up here. So let's copy these down here. I'm going to copy this whole surface down here. I'm going to get the surface closest point again. Oh, the surface. And I'm going to get the area for the centroid. Now, if I evaluate that surface, this surface and the UV point, it gives me a normal direction. Turn some of these off. So if I have a normal direction, I can start to consider the slope a little more specifically. So what do I need? I'm going to make a vector from this normal. Let's do a vector display from that point and that normal. And you can see that these are all pointing down from that point. But if we want to show the slope, we want to show the direction along that surface, right? So let's use some of our vector math. We can do a cross product. We have this normal direction. We have a, say, z direction, what's pointing up. So this should give us something perpendicular to that. If I use a new one, that should be parallel lines that are pointing sideways. So this is kind of like our contours of each one of these. I'm going to see how they move around the peaks. Now if we take another cross product, of this line and the normal, instead of giving us down perpendicular to that, it's down along that surface. So that should be actually the direction that everything's sloping. So let's see if we can visualize that a little bit more. So I'm gonna make an amplitude for this. Let's make it 8. Turn off some things so you can see how, say, water might flow off the surface. Now, if you don't understand these cross products, it's basically taking something that's pointing directly up the z vector and the normal to that surface. It should give you a perpendicular to those two, gives you the sideways vector. And so a sideways and the normal vector gives you something that faces down along that surface. Okay, so let's use some of our calculations to be able to have more understanding of that. So what happens if we only want to color code certain areas of that slope? So what we can do, instead of using the vector display like this, there's another vector display that has a little more, a couple other options. So we can give a point, we give a vector, we can also give it a color or a width, so we can change those independently. So I'm going to take this vector, and then I'm going to unitize it. Just make it all one again. And then I want to somehow put it within a range that allows me to change the color values. So let's see what we can do. We can deconstruct that vector. The length, if we say make a new vector that just has the x and y, so we're not pointing down, but we're just pointing out from that, it'll tell us how much it's sloping, right? We have rise over run. If we want to find that slope, we have a vector. We need to find its rise, which would be the z value of that vector, and then the run, which would be the x and the y vector. So what we have right now, the z component is the rise. The x and y component together would be the run. So the slope would be rise over run, the length of this one. So z component length and the length of the run. That should be our slope value. Now the slope we want to be positive. So we're going to find the absolute value for this one. So the positive slope. So let's remap this in terms of color now. Let's find the bounds. Bounds are between 0.008 and 4.6. So if I remap these numbers, take this result and this source and remap them, and I'm going to use a color XYZ. So I can take this value. Let's see what this does. I'm going to plug these into the x and y, or sorry, the y and the z. So it gives me this nice sort of blue color to represent the water. And the higher the slope, the brighter the blue it is. Now I can also take this remapped color and use it to adjust the width. So maybe multiply this by some value that makes sense. Let's give it a multiplier. So we can turn that remap scale into a width scale. So the ones that are too small show up really tiny. Ones that are large enough actually show up just where we have the slope region. It's interesting to differentiate that a little bit. So then that shows us areas of most curvature and areas with the most slope, runoff directions. Let's do one more thing. Let's test a couple points throughout this surface and give some annotations to that. So to do that, let's go back to this. Let's go back to the surface and populate it with a couple of points. I'm going to populate geometry. Let's use our original surface over here. And let's make 25 test points along that surface. Now, if I were to evaluate that surface, I can get the normals again. So I can get the surface closest point and use these points. I'm going to use this surface. And maybe I'll bring the surface down here so you can see what I'm connecting to. Surface closest point, and then I can evaluate surface. The surface, and I have the UV point. Gives me this normal again, just like I was doing before, except I'm using the larger surface, not the individual surfaces. And so from there, I need to get a line to use for my annotation. So let's make a SDL line, which is a line that has a start, a direction, and a length. I can take these points as the start. I can give it a normal direction, and then I'm gonna give it a length as well. So I'll just say 70. Now those are all pointing down, so I don't want that. We're going to reverse this so it points up. So I have some lines that I can use as leaders for my annotation. Right? So something I can do this in many different ways. I can use a marker dimension. So it just needs a line. It needs some text. And it needs a size. So let's say the size will be 3.25 or something like this. Text right now is a generic text that goes in there. If we give it a slope, our slope we already have. We've calculated it up here, which is this. Where did it go? This absolute value is our slope. So we put that in as the text. So that gives us a slope for each one of these. Now this slope doesn't mean a whole lot. Let's see if we can put it in a better sort of format. So I'm going to use an expression. And I only need one variable. I'm going to take this variable. In this format, the expression, the standard format would be to the standard expression would be to format this geometry in some the x and y in some way. But we're going to use that. We're gonna format our value to 2 decimal places. You know, I have one of those values. And we're also going to then multiply it by 100. So let's see if that's correct. Something's off about that. Do this again. Format. Oh, same thing that was happening before, I believe. Let's change this to an X and see if that helps. Okay, so our X variable is coming in. It's changing the format so that it only has 2 decimal places and it's multiplying it by 100. So if we put that into our text, it should adjust it. Oh, I also added the percentage behind it. So we say, okay, an 8.79 percentage for each one of those. Now it's kind of difficult to read some of these going vertical like that. We also don't have that many slopes. So this is 28,000, and we're only using 25 of them. So we need to make sure that we're getting the right number of calculations, and those calculations are correct. So see, if we want to do that, we want to see what the closest index to these points are. So let's see. If we have a closest point between these points right here and all of the points of the bricks, the centroids of the bricks, it should give us an index. So the closest one should determine that slope. So then we can pull out an item from that. So we can say out of these absolute values, we just want to pull out these indices. It should only be 25 because that's how many we have. So we plug that into it. Now everyone should be associated with the right place. So this point is actually the slope of this brick right beside it. It's the closest one. So it gives us a roundabout way of measuring that. Now, other than the marker, we can make other things. We can make a tag, text tag, which has the same sort of location can use an endpoint. Here's our text. Sorry, let's use the endpoint of this. Now if we wanted to, we could move that point up off that line slightly. To give them a little more control over how that looks. We can also use a 3D text tag. So this one will rotate and always face the camera. This one will take that location and that text. We'll plug in a size. We could also give it a color if we wanted to. And something this does is it always faces a specific plane. So there's three-dimensionality to it. Now if we want it to face the same way, we can give it, say, an XZ plane at that location. But it doesn't face the camera, which might be useful in some scenarios. It also has a justification, so we can set it to being on one side or the other. Depending on where you want it to be. So we can use that to build a pretty interesting sort of diagram that represents multiple types of information and analysis, and allows us to build that sort of directly on our geometry. So hopefully we can use that in future cases not only to analyze, but then also to generate new forms and new ways of working with that geometry. That's it.